Okay, Calcers, here we go into the home stretch here of section 5.2. So what we're doing right now then is pretty high on the practicality scale, whereas a lot of what we've done so far has been kind of theoretical. Properties of the definite integral. So these are some of the things that I would say you're going to look back on later and go, oh yeah, this is how I actually evaluate integral problems. But the truth is most of these are going to become so plainly ingrained in the way that we do things that you're going to know this stuff pretty straight up and pretty easy. First of all, integral of a constant. If we are taking a definite integral, that's not what it's supposed to look like. If we are taking a definite integral, here we go from a to b, and if our integrand, instead of being a function like f of x, is simply going to be a constant. So we'll go ahead and put c there, but the important thing is this dx tells us that c is not a variable in this problem. X is the variable we are integrating with respect to. So since our integrand right here doesn't contain the variable x at all, we know that this is integrating a constant as opposed to some other function. Okay, and what that one tells us then, guys, if we think about what this looks like from a graphical standpoint, humor me for just a second, we're integrating a constant function, which we kind of did on a previous example in one of the other videos. So in a constant function, you'd have the line y equals c, which would be a horizontal line. That's what's important here. Y is equal to c, and we're starting this integral somewhere here at a. We're ending it a little bit further to the right somewhere at b, and that is going to give us a shape right here, you guys, that in this one case, the way I happen to draw it, kind of looks like a square. But I can't say that that's always going to be a square. It is, however, always going to be a rectangle. And the area of a rectangle is always its base times its height. So the base of this rectangle is that delta x right there, the gap between a and b. So we're always going to take our right endpoint, because that's always going to be the greater number, b, and subtract the left endpoint, which is always the smaller number. So that quantity, b minus a, gets you the width of your rectangle, and the height of your rectangle is just determined by the value of this c right here. So c times the quantity b minus a is going to get you a quick little formula there for the integral of a constant. Honestly, that's a formula that I don't feel like year to year people really learn all that well. Okay, I think it's one people just kind of figure their way through and they go, yeah, well, that's not too bad. All right, the sum and difference rule is another one of these that's pretty intuitive, guys. The definite integral here from a to b of either the sum or the difference of two different functions, f of x plus or minus another function, g of x, and we're taking all of that with respect to x. Now let me say for just a second that to indicate that we are integrating the entire thing here, the sum or the difference of those two functions, it certainly would not be a bad idea to use brackets or parentheses or some type of grouping symbol around the f of x plus or minus g of x. However, you usually won't see that notation, and the reason why is it's unnecessary. The integral right here tells you that what comes immediately after that integral sign is the beginning of your integrand. And the dx here at the very end, that's the end of your integral expression. So it's kind of implied then, you guys, that everything in between the integral sign and the variable of integration, that's your integrand. So while it's certainly fine, not wrong at all, to put parentheses or brackets there, it's unnecessary because the integral sign and the variable of integration accomplish the same purpose. Now, back to this. The sum or difference rule, this is going to be a little bit tight to fit in here, guys. It simply says, and lucky for you guys here, the same thing that a similar rule said for limits back in Chapter 2, and that it said for derivatives back in Chapter 3, that an integral of a sum is equal to the sum, or in this case, or the difference, of the individual integrals. It says that you can do an integral just from a to b of the first function, f of x, but don't forget your limit, your variable of integration there. So the integral of the first function, and then plus or minus the integral from a to b of the second function, g of x, taken with respect to x as well. So once again, everybody, this rule, the sum difference rule for definite integrals, tells you that the integral of a sum is equal to the sum of two individual integrals, or the same thing applies to differences. This is what allows us to integrate a polynomial function term by term, exactly the same way we did with limits, exactly the same way we did with derivatives. All right, moving right along here, guys. The last rule I believe that I have for you on this page is the constant multiplier rule. And again, this looks very similar to something that we did with limits and with derivatives. A definite integral from a to b of a function being multiplied by a constant. So c multiplied by a function, f of x taken with respect to x. Well, this rule says that everything that's going on here is related to the variable of integration, which is x. So f of x, obviously, because it has an x there, has to do with x. And these limits of integration, a and b, are the lowest and highest values of x within this range. But you'll notice that the c, the constant, has nothing to do with x at all. So once again, this rule tells us that we can pull the constant out in front and then do all the business that we really need to do. So this is c times the definite integral from a to b of f of x taken with respect to x. This is a rule that we are going to use a lot, everybody, later on this year to try to simplify some relatively complex integrals that we may have to evaluate by hand. And I'll tell you right now, not that it's going to matter, the most common constant that we're going to be pulling out in front of an integral is pi. We're going to start doing something called solids of revolution, where you spin things around an axis to make a three-dimensional solid. So anything circular is going to have pi in there for area or for volume, and we tend to pull that out in front quite a bit. Okay, so that was C, the constant multiplier rule. Looks like I skipped one right here. There we go. D, reversing the limits. This is a property that's not super hard to understand, but a lot of people then kind of wonder, well, why would we do that? And I got to tell you, this one will come up kind of organically, and you'll see it at the time, and I'll go, oh, remember that property? You guys didn't think we were going to use it at all. And here we go. If we take a normal integral here, definite integral from a to b, of f of x with respect to x, okay? And we want to compare that, everybody, to the same integral except with the limits reversed from b to a of the same integrand here, f of x, taken with respect to x. The question is, what's the relationship between those two integrals? Well, the way we set it up normally, working from a to b, your delta x then, the width of each rectangle, worked from the b direction back to the a direction. A greater x value minus a smaller x value, and that always gave you a delta x or a dx that was positive, because we're taking bigger number minus smaller number. But now that we reverse the limits over here on the right side, the dx or delta x, the width of each rectangle, is going to look here first for a smaller number and then subtract a larger number from it to get the width of that rectangle. And anytime you take a smaller number minus a larger number, this is a little bit weird, but your width of your rectangle is actually going to end up being negative. Now the heights of your rectangles, f of x, they're exactly the same. So by reversing the limits, okay, what happens is that the area of each one of those rectangles, now at least mathematically, comes out negative. So what we see here, guys, is that one of these integrals is equal to the opposite, I don't like how I drew that, is equal to the opposite of the other. Okay, so either way you want to do this, you could put the negative on either side of this equation. But what's important to note there, everybody, is that if your limits of integration switch, if they're not in the order that you would normally like them to be, you can flip them back, but you've got to put a negative out in front of that whole thing. Again, that's a difficult one to understand just when we think about it theoretically. When we see it in practice, I think it'll make a little bit more sense. This last one I think is pretty obvious. If you have an integral here with the same limits of integration, like from a to a of some particular function right here, f of x taken with respect to x, well, if you go back and think about what we're trying to do here with a definite integral, we're trying to find the area in between a curve, f of x, and the x-axis, starting at, on the left, your lower limit of integration, ending on the right, at your upper limit of integration. So what happens here? we've got a curve. It does something like this. You're going to begin measuring area right here at A, and instead of ending it over here somewhere at some other value that's B, we're instead going to end it right there where we started. And what happens, guys? We don't have a region. What we have is a line segment, and the area of that line segment, hopefully your geometry teachers taught you this well, is 0. So anytime you've got the same limits of integration, it doesn't matter what's going on here, but as long as the lower and upper limits of integration are the same number, you'll always end up with 0. All right, that was E right there. Let's take a look at F. Okay, the additivity property for adjacent intervals. All right, adjacent meaning right next to each other, everybody. So real quick, I don't think I need to spend too much time drawing this out, but if you had a curve, doesn't really matter what the curve is, and it looks something like that. If you had one interval that maybe started right here at A and then went over here to B, and then you had a second interval now that was adjacent to the first interval. So I'll call that interval number 1. And for region 2 to be adjacent to region 1, it has to begin right where region 1 ended, which is at B. So if I put another value over here and call that C and said, okay, there's region 2, you might already see where I'm going with this, guys. The additivity property says that if you're going to take the area of region 1, which is the integral from A to B of whatever your function is, f of x, taken with respect to x. So that'll get you the area of region 1. And add to that the area of region 2, which is the definite integral now, starting at B and ending at C of f of x with respect to x. That could be more conveniently or more efficiently expressed as one big integral starting right here at A and going all the way to C. So we could just make that the integral from A to C of the same function, f of x, taken with respect to x. And you can apply that property in either direction, guys. There's a reason that equal signs are symmetric right there. You can read them left to right or right to left. Various problems have different applications of that concept right there. And the comparison theorem is just a little bit weird, not real high, everybody, on the kind of the usefulness scale. But because it's a theorem, we tend to write it in if-then form, guys. So what we would need to say is, let's try this again, if there is an established hierarchy between two functions, all right, if we know, let me go with this, guys, that g of x is greater than or equal to f of x, on some interval here from A to B, and I'm going to include the endpoints here as well. So if we know that g of x is always the greater or higher function, then it must be the case, everybody, that the integral from A to B of the higher function, which in this case is g of x, taken with respect to x, must be greater than or equal to the integral from A to B of the lower function, f of x, taken with respect to x as well. And I'll spare you the whole demonstration right here, but that works, everybody, if both of the functions are positive, it works if both of the functions are negative, and it works if one is positive and one is negative. In any one of those cases, if we know g of x is always above f of x, then the integral of g of x always has to be greater than the integral of f of x. All right, guys, those are the, 7 properties, or one theorem right there, that we had to talk about. Now we kind of blur the line right here between kind of practicality and working theoretically right here. So for this last section, I don't know why I didn't put a number at the top of this here, guys. Let me think. That was number 4. I guess I should have called this number 5. Sorry about that. All right, real quickly, integrals to memorize, and I do say for now, because pretty darn soon, like within the next couple of sections, we're going to learn how to actually compute these integrals, and it's not going to be very difficult. So you're not going to need to have these memorized forever, guys. But basically, 2 things that are going to help you, and really kind of a concept more, that's going to help you through the 5-2 homework. The integral from 0 to b of x squared is equal to b cubed over 3. So if you think about, practically speaking, what's going on, the function we're dealing with is y equals x squared, which we played around with a lot in our notes, everybody, in section 5.1. So if we had the function y equals x squared, and we were measuring an integral here starting at starting at 0 and ending over here at an x value of b. All right, if we're looking for the area underneath the curve y equals x squared from 0 to b, this simple expression right here will give it to you, guys. That integral then is b cubed divided by 3. And let me stop for just a second. Do we want to? I'm not going to write it down. But back in the 5.1 notes, we spent a lot of time trying to approximate the area underneath y equals x squared on the interval from 0 to 3. And if you guys recall, we did it with the left endpoint approximation method. We did it with the right endpoint approximation method. We did it with midpoints. We did it with trapezoids. We did it a lot of different ways. And the answers that we came up with were all a little bit different, guys. But I'm trying to remember exactly where they were. In fact, if you can't tell, I'm stalling right now because on my laptop, I'm trying to look up some of the answers that we came up with. Most of them, let's see, we had some small answers. Like, for example, our left endpoint approximation method was, come on, computer, any day now. Let's see. No, that's not it. That's not it. That's not it. No, now I can't find it. No, 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 no. Okay, here we go. L6, everybody. We came up with a left endpoint approximation of what? 55 over 8, which is just under 7, 6.875. In fact, I'm going to write that down real quick. 6.875. We came up with a right endpoint approximation of 11.375. And we had reason to think that this one was too low and that the second one was too high. We came back and did it again with a midpoint approximation and got 8.9375. Then I believe we did it once more with trapezoids and got 9.125. So those were all the answers that we came up with 4 different approximation methods. If this formula that we just wrote down is to be believed, then the actual answer right there, everybody, would come by taking b cubed over 3. b is your upper limit of integration if you start at 0. Well, that's what we did here, guys. We started at 0. Our b value was 3. So if I plug a 3 in here for b cubed is 27. 27 divided by 3 is 9. That means that the exact answer that we were looking for in those problems was 9. Our left approximation was too low, our right approximation was too high, but it kind of looks now like the midpoint approximation and then the trapezoidal approximation right here were both pretty darn close. But the weird thing about this is, everybody, and I don't know about you, this freaks me out just a little bit, is that the area underneath that weird irregular curve right there might actually end up being something really, really nice, a clean, rational integer number like 9. All right, I don't want to get too far ahead of myself. Too late. A second integral now to memorize for now was that the definite integral from 0 to b of x cubed is equal to b cubed over 4. I'm not going to talk any more about that one. I'm just going to have you guys write that down. And now I'm wondering at this point, you guys, if we aren't starting to see a pattern already to what's going on. So if I were to ask you all, let me go back to black right here. Hey, let's take a wild guess on the integral from 0 to b, and look at your integrands now. X squared, then x cubed. Now let's try making it x to the 4th, taken with respect to x. If you had to guess what that would be, most of you would look at that and go, oh, I get it. This is going to be b to the 5th over 5. And you'd be right. And an integral from 0 to b of x to the 5th, taken with respect to x, well, you guessed it, that is going to be b to the 6th all over 6. So we're kind of starting to see some patterns developing right here, and those patterns are going to be part and parcel of how mathematicians figured out how to actually compute definite integrals very quickly and very efficiently. We're really not there yet in section 5.2. 5.2 really isn't teaching us how to compute integrals. It's just showing us a new notation that we can write a definite integral because it's a more efficient way of writing an infinite summation. Okay? Later in 5.3, we'll talk about the big realization that this was actually something we could do quickly. But as I said, we are not there yet. Now, I am reticent to show you slide 11 at all, but let's go ahead and look at it right now. All right. I left this all worked out from a previous year. I really don't think that you guys need to write this down. I'm going to talk you through it, and I'm going to try to not talk too long here. So, okay, I guess I did a number 5, so now I needed to make this a number 6. All right, sorry, guys. Math is hard. All right, and what we're trying to do here is prove, there's a word you love to hear in math, prove that the integral from 0 to b of x squared dx is equal to b cubed over 3. That is the first little formula that we wrote down on the last slide. So, how can we do that? In line number 1 right here, we're going ahead and we're taking this definite integral here, the one that we're trying to prove eventually is equal to b cubed over 3, and we're going back to the first slide and we're working backwards. We're going from this efficient notation of the definite integral back to where we started, which is writing everything out as an infinite sum. So, the integral, everybody, gets replaced by the limit as n approaches infinity of a summation starting at j, not sure why I used j here instead of k like I did last time, but whatever, starting at j equals 1 and going up until n. Now, it's messy, but this expression right here, f of a plus j times delta x, that is the height of each one of your rectangles. A, you'll notice here, is the beginning x value, and then we're adding j, which starts at 1, times delta x. What we're doing here, guys, is a right rectangular approximation, and the number of rectangles is just given to us by this n up here. So anyway, f of a plus j times delta x is the height of each rectangle. Delta x is the width of each rectangle. So now let's move on down here to line number 2 and let's see. This whole mess here is the same, nothing changed, but what's different? We replaced the a with a 0. Why? Because a is always your lower limit of integration, which for us in this case was a 0. J is the sliding variable of the sigma, and then the delta x right here, guys, is b over n. I've got to remind you guys of a little formula we wrote down in 5.1, that delta x is equal to the width of your overall interval, which is b minus a, over n. Well, in this problem, a, the lower limit of integration, is 0. B, the upper limit of integration, is just b. So this expression I just wrote in red becomes b minus 0 over n. So b divided by n becomes the value here for delta x. And that's why we use that right here, but also right here as well. Okay, so moving right along, let's see where we're at now. So that's line 2. What is happening now that's different in line 3? Again, the limit, the infinite sum right here, the limit as n approaches infinity of a summation from 1 to n, that stays the same. Now, in the parentheses, though, the 0 is something that we're adding so we can ignore it, and j times b over n just becomes jb over n. Everything else is the same. Guys, the point I'm trying to make here is that I understand that as high school juniors or seniors, even though we're pretty darn smart people, you guys are not high-level mathematicians at this stage of your life. Relax. I wasn't at your age either. I don't even know that I am now. But my point there is, a lot of you guys are going to look at this and say, oh dear God, I can't understand what's happening on this page because reading math is difficult. And you're right about that. But the point I'm trying to make here is that if we only zoom in, literally, okay, on one step at a time, a lot of times you can understand if you just go from one step to the next by simply asking yourself, what is different and why is this okay? So let's move from step 3 to 4, all right? The limit as n approaches infinity of the summation, so the infinite sum stays the same. Now, what else is the same? The b over n at the end is the same, but this little part right here has been replaced here. F of jb over n has been replaced by this. Well, let's remember, guys, f is just our function in this problem, and the function right here is y equals x squared. So whatever your input value was right here, you're simply going to square that input value, and that's the value of your function. So jb over n squared is going to get us j squared b squared all over n squared. So that's the change here. And again, I'm hoping we can see this just by looking at it one step at a time. Okay. On to step 5. How did we get to step 5? From step 4. Okay, what's the same? Once again, the infinite sum hasn't changed at all. And now, this entire product right here, j squared b squared over n squared times b over n, gets replaced by j squared b cubed over n cubed. All we did is we multiplied those two fractions together. You guys can all understand that. Okay, so that gets us to step 5. Now, step 6, let's see what happens next. How did we get here? What's different from 5 to 6? Well, the weird thing about this now is that this b cubed over n cubed is now in between the limit and the sigma. And they took out the b cubed and the n cubed here, and all that's left now after the sigma is the j squared. Here's what's important about that, guys. The variable of the summation is j. That means that the only, out of j and b and n, the only one of those three variables that's impacted by the sigma is the j. Everything else, the b and the n, can get pulled out in front of the sigma, and that's why we put those factors right there. Notice I didn't pull them out in front of the limit, because the limit right there, guys, does relate to this n variable, but I was able to pull it out in front of the sigma. All right, and where are we now? This is going to be a weird spot, and it's using a fact that probably 50, 60, 70, 80, 100 years ago, good level mathematicians knew. And you guys don't now because we have no reason to know it because we have other ways of doing it. But this expression that I've put the green box around, guys, the summation from j equals 1 up to n of j squared, there's a formula for that. And a lot of older math books would have had that formula written down in them. So, to get from line 6 to line 7, you'll notice that the beginning of it now stays exactly the same. But what was in the green box, that summation, now gets replaced by this quantity right here. And unfortunately, I'm going to ask you guys just to trust me on that one. Well, don't trust me. I didn't do the math to figure that one out, but that's an established identity, that this summation right here can be expressed with this trinomial expression there, n cubed over 3 plus n squared over 2 plus n over 6. Right? Right. We're all going to go with that. Now, where are we next, guys? This now becomes a limit as n approaches infinity, and the sigma's gone, of b cubed over n cubed times the quantity n cubed over 3 plus n squared over 2 plus n over 6. And now that the sigma is gone, we are going to redistribute the b cubed over n cubed back into this trinomial expression right here. All right, so how do we get then to step 8? Well, we distribute it. So again, the beginning now, the limit as n approaches infinity stays the same, but now we end up with, let's take a look, the n cubes cancel here on the first term, and we get b cubed over 3. 2 of the n's cancel, and we get a b cubed over 2n on the second term, and then 1 of the n's cancel at the end here, and we get a b cubed over 6n squared. We're taking the limit as n approaches infinity of that trinomial expression. And what I need you guys to remember here, n is the variable and b is a constant. So as I go to step 9 right here, as we let n approach infinity, that has no bearing at all on the value of this first fraction, b cubed over 3. But in the second fraction, if we remember that b is a constant, that means our numerator is a constant. But the denominator, because it contains a factor of n, increases without bound. And as your numerator stands still, but your denominator continues to grow, the limit of that fraction is equal to 0. And the exact same thing happens over here. That becomes a fixed constant divided by a growing denominator. That becomes 0 as well. And so, everybody, we've gone ahead now and we have evaluated that limit, and we end up with the result that we were seeking. We were trying to verify of b cubed over 3. Woo! Hey, I have good news for you. That is not something you will ever need to do on your own. It will not show up on a homework question that I'm going to give you. It won't be on a quiz or a test or the AP test or your college entrance exam or the math test you have to take to get into heaven when you die. I hope there's one of those. Anyway, the point there is this is just kind of a theoretical exercise because at this level of math, we hate telling you guys, hey, here's a thing, believe me. We want to actually show you guys why it is that that works. And so that's what I was hoping that we kind of, sort of, maybe a little bit accomplished with this little exercise right here. Okay, so hopefully that makes a tiny little bit of sense. Let's do one example, and then finally, ladies and gentlemen, we will be done with this long section of notes, and you guys can get working on your homework. Now, this would be a problem right here that I think you guys are going to whip through pretty quickly, but I want to kind of talk about how we can do this properly using some of the properties that we've discussed here today. A definite integral from 0 to 4 of 2x squared minus 5 taken with respect to x. Okay, so let me write this out here one more time. Definite integral from 0 to 4, and you'll notice this only works with an integral that starts at 0 because all of the properties that we learned here had an a value of 0. We'll talk about how to tweak that a little bit later, but for now I think we're good with that too. Again, I told you before, you don't really need the parentheses right here because the integral sign and the variable of integration kind of accomplish the same thing. All right, guys, the very first thing we're going to do, I'm going to go slowly here, I'm going to use the sum or difference rule that says that an integral of a difference is equal to the difference of the two individual integrals. So that's the integral from 0 to 4 of 2x squared dx minus the integral from 0 to 4 of 5 dx. Now again, this is something you will normally do intuitively and you won't need to make a big stink out of it, but for now we're going to run with this. Okay, this is getting closer to something that I know, but I'm going to now use the constant multiple rule and pull that 2 out in front. So this is now 2 times the integral from 0 to 4 of x squared dx minus, now let's take a look at what's going on here. This is the integral from 0 to 4 of a constant. And the integral of a constant property we said I talked about a while ago said you could evaluate this integral by taking b minus your a value multiplied by your c constant value, which is 5. That expression right there, guys, is the area of this rectangle. The base of that rectangle, 4 minus 0 is 4. The height of that rectangle is 5. Now, moving on down to the next line, the 2 stands still, and now we multiply that 2 by the value of an integral from 0 to 4 of x squared. Well, that's a formula. I missed it. There we go. That's a formula that we have right here, guys. The integral from 0 to b of x squared dx is b cubed over 3. So here we go. Our b value is 4. So that's going to be 4 cubed over 3. That takes the place now. That is the value of that integral. Minus, and we'll go ahead and finish up the right side of this. 5 times 4 is just going to be 20. And now it's just some pretty simple arithmetic to knock this out, although this doesn't work out great, but that's okay. The 4 cubed is 64. The 64 times 2 is a 128, and that doesn't divide evenly by 3, so that's just a 128 over 3. Minus, I'll go ahead and turn that 20 into a 60 over 3, so I have a common denominator, and it looks like we're going to end up with our answer now, guys, of 68 over 3. There's nothing else to do here. You don't have to write square units because it's really not an area problem, and that doesn't divide out at all, so we're going to be perfectly fine leaving the answer as an improper fraction of 68 thirds. Okay, there's certainly more to talk about here, but I think you guys will do well to just start the homework and see what questions come up. I feel like you've got a lot of information here, on 5-2, and you're going to be okay moving forward. So let's give that homework assignment a try. Good luck on it, and let me know when you guys have questions.